Hello everyone, welcome to the final lesson for Chapter 2 of the Foundations of Scalable Systems. In the previous lessons, I've explained how we can scale out the processing and data tiers in our system to increase its capacity. The basic approaches employed are foundational to scaling an application. However, if you think about physical buildings, we don't increase the capacity of an office block or a hotel by increasing the space on the ground floor. We stack floors on top of each other and create pathways between them. We do the same in software systems. Any realistic system that you need to scale will have many different services that interact to process a request. For example, accessing a web page on Amazon.com can require in excess of 100 different services being called before a response is returned to a user. The beauty of the stateless, load-balanced, cached architecture that we've elaborated in these lessons is that it's possible to extend these core design principles and build a multi-tiered application. In fulfilling a request, a service can call one or more dependent services, which in turn are replicated and load-balanced. There are many nuances in how these services interact and how applications ensure rapid responses from dependent services are achieved. Again, I'll cover these in detail in later lessons. This design also promotes having different load-balanced services at each tier in the architecture. For example, the illustration on the slide shows two replicated internet-facing services that both utilize a core service to access the database. Each service is load balanced and employs caching to provide high performance and availability. This design is often used to provide a service for web clients and a service for mobile clients, each of which can be scaled independently based on the load they experience. It's commonly called the back-end for front-end pattern. In addition, by breaking the application into multiple independent services, you can scale each based on the service demand. If, for example, you see an increasing volume of requests from mobile users and a decreasing volume from web users, it's possible to provision different numbers of instances for each of the services that handle the mobile and the web users to satisfy the increasing demand. This is a major advantage of building applications as multiple independent services, which can be separately built, tested, deployed, and scaled. I'll explore some of the major issues in designing systems based on such services, typically known as microservices, in a later lesson. Now let's look at responsiveness. Most application requests expect some form of response. A user might want to see all auction items for a given product category, or see the real estate that's available for sale in a given location. In these examples, the client sends a request and waits until a response is received. The time interval between sending the request and receiving the result is the response time of the request. Our systems want to minimize this response time. You can do this by using caching, but many requests will still result in relatively slow database accesses. A similar scenario exists for requests that update data in an application. If a user updates their delivery address immediately prior to placing an order, the new delivery address must be persisted so that the user can confirm the address before they hit the purchase button. The response time in this case includes the time for the database update, which is confirmed by the response the user receives. Some update requests, however, can be successfully responded to from your application without fully persisting the data in a database. For example, when your driving app sends a new GPS location to its mapping service, it doesn't wait for the new location to be persisted in a database. The app will send the new update in the knowledge that it will be recorded by the system and be available for viewing at some later time. Your service implementations can exploit this type of scenario to improve their responsiveness. The data about an event is sent to the service, which acknowledges its receipt and concurrently stores the data in a remote queue for subsequent writing to the database, as shown on this slide here. Distributed queuing platforms can be used to reliably send data from one service to another, typically but not always in a first-in, first-out FIFO style fashion. Writing a message to a queue is typically much faster than writing to a database, and this enables the request to be successfully acknowledged by the service much more quickly. Another service is then deployed behind the scenes to read messages from the queue and write the data to the database. When the user eventually checks that their data has been received, maybe a few minutes or a few hours or a few days later, the data has been successfully persisted in the database. There's a collection of queuing technologies that exist that you can use in your applications, and I'll discuss how these operate in later lessons. Basically, they all provide asynchronous communications. A producer service writes a message to a queue, which acts as some form of temporary storage, while another consumer service removes messages from the queue and makes the necessary updates to some downstream database. The key is that the data is eventually persisted. Eventually typically means a few seconds at most, but use cases that employ this design should be resilient to longer delays without impacting the user experience. So that's it for our whirlwind tour of the basics of scaling a software system. The devil, of course, lurks in the details, and later lessons are going to dive into those murky details to shed light on algorithms and system design approaches that facilitate scalability. Thanks again for watching.